Hi, I'm LIN from Taipei First Girls High School, and my research is about the degradation of RPLA, recycled PLA, with the non-metal catalyst PLA-DEG and its application in Vitrimer synthesis. So why do I want to do a research on PLA recycling? Reports from European Bioplastic Association suggest that around 2.4 million tons of bioplastics were produced worldwide in 2021, and this number will definitely increase up to 7.5 million tons in 2026. PLA is the most widely used bioplastic, but it requires specific conditions to be degraded in a short period of time. The slow degradation, increasing production, and the lack of proper disposal further leads to the accumulation of PLA wastes. How can I recycle it in an eco-friendly way? And also, can I reuse it into valuable products? In my research, I provide a pioneering solution. That is by degrading PLA into lactodiol with the newly developed organocatalyst PLA-DEG. Subsequently, lactodiol will undergo polymerization, chain extension, and molding to form itself as Vitrimers. You may ask, what is Vitrimer? Vitrimer is a material that combines the rigidity of thermosets and the reprocessability of thermoplastics. At high temperature, it behaves just like viscoelastic liquid, and at low temperature, it's just as rigid as thermosets. The most important property for Vitrimer is that Vitrimers are repairable, which means that we can reprocess the Vitrimers all over again, and therefore the life cycle of PLA waste can be elongated. So in the degradation part, a powerful and cost-effective catalyst is essential. To understand the real-life challenges when we face in the recycling process, I choose the recycled cups rather than PLA pellets as the starting materials, and cut the cups into small pieces for degradation. PLA-DEG is a Lewis-based non-metal catalyst, which promotes proton exchange and therefore speeds up the transesterification. How transesterification occurs is that the lone pair on the hydroxyl group will attack the carbon on this carbonyl group, and the electron transfer, and PLA-DEG can speed up the electron transfer process. So here's how I know that PLA had been completely degraded within 15 minutes. The upper spectrum is the NMR spectrum of the starting material. So by comparing these two NMR spectrums, it's obvious to see that the two peaks located at 1.5 and 5.2 ppm have completely disappeared after 15 minutes. The peaks from lactodiol, as you can see here, can be clearly assigned. That means the degradation is completely and successful, reaching an over 99% yield of lactodiol within just 15 minutes. So the graph on the left shows the dosage effect, which means the amount of catalyst will affect the time needed for complete degradation. PLA-DEG is critical for the degradation. Without it, PLA cannot even be degraded even after 3 hours. But with PLA-DEG, PLA can be fully degraded within just 15 minutes under 150 degrees Celsius. Now, how do I know that PLA-DEG is really better than the other catalysts proposed by previous studies? It's better than the other catalysts in 3 aspects: more eco-friendly, more effective, and more efficient. It's more eco-friendly because it does not contain any metal ions. It's more effective as shown in an over 99% yield of lactodiol, the monomer. And it's more efficient. PLA can be fully degraded within just 15 minutes. Compared with others, PLA takes 240 minutes to be completely degraded. That's a huge difference. So in the polymerization step, I've tried 2 methods. and both are successful. The one is without chain extender but with catalyst. The catalyst is zinc acetate. And the other one is with chain extender but without catalyst. So here is important to note that the chain extender is used for increasing the molecular weight. During polymerization, the mixture slowly changes from being fluid, viscous to glassy. In some cases, the viscous mixture, which is the mixture of medium viscosity, will further undergo chain extension to increase the molecular weight. And after chain extension, the propolymers will gradually become glassy, and lastly, only the glassy propolymers will be taken to heat press and form themselves as vitrimers. For Vitrimer engineering part, I've tried two methods. The first one is direct casting, and the second is heat press. Direct casting is an economical method that can be applied to the mass production of filming. And heat press also has its advantage. It is pretty good. Heat press enables to produce vitrimers with high efficiency under consistent reaction conditions. And consistent reaction conditions is really important for me to produce various vitrimers with same good qualities. And after the vitrimers are formed, I further test the repairability and the gel content. Repairability is important because if it's repairable, it can be reused and the life cycle of PLA waste is elongated. So how did I test the repairability? I cut the sample into pieces and further reprocessed through heat press method, as you can see the picture on the left. And the results turned out to be positive. The model can be reformed, and also the tensile strength is just as good as the pristine model. And gel content reflects the cross-link density of the vitrimers. So that means if the polymerization step is completed and more successful, the gel content, the cross-link density of the vitrimers will be higher. And as you can see here, the gel content of the samples are all around or even above 90%, which means the polymerization step is completely, and it can be further used for heat press. Here's the Vitrimer engineering part, and it shows how I test the tensile strength of the Vitrimer models. The tensile strength is tested by the machine in the middle is called the universal tensile machine. And before we get into the stress strain curve on the right, let's just first talk about the formulation design. I adjust the formula to make the vitrimers both repairable and rigid. So, to be repairable, there must be excess hydroxyl groups to perform transesterification under high temperature. And to be rigid, the ratio of OH groups from diol, which is the degraded product, to tetraol, the cross-link agent, the cross-link agent will make the vitrimer to be rigid. The ratio of diol to tetraol is really critical. And the optimized condition I found is when the OH groups to carboxyl groups is 1.02 to 1, and the ratio of OH groups from diol to tetraol is 1 to 1.42, as shown in the Model C, and which is also the same as the orange curve shown here. So by adjusting the formulation design, I found the vitrimer of highest rigidity. But if we want materials of higher flexibility, because we don't always need materials that are so rigid, just simply adjust the ratio of diol to tetraol, and I can create all sorts of materials either with high flexibility, medium rigidity, or really high rigidity. It's also important to note that the decomposition temperature for model A to E are all around 200 degrees Celsius, which means that it will not decompose under room temperature and can be used in daily lives. And the glass transition temperature for A to E are all below 30 degrees Celsius, and that means that they are all of low volatility and can be safely used. To sum up, what makes my research stand out is that the eco-friendly non-metal catalyst PLA-DEG significantly speeds up the degradation process. PLA can be degraded within just 15 minutes under 150 degrees Celsius while also reaching an over 99% yield of decadiol. Also, Vitrimers of great mechanical properties and repairability are obtained. Once quantities of PLA waste are thrown away, we now have a concrete and practical solution to transform the PLA waste into valuable products. And that's all for my research. Thanks for listening.